Alright students, Assalamu alaikum. This is Talha bin Nadeem, and I would be teaching you guys internal combustion engines along with the Dr. Usman in this semester fall 2020. As you guys must have attended all the previous lectures which were recorded by the Dr. Usman Lodi. You guys started with the basic concepts and the basic components of the internal combustion engines, and then in chapter number 3 you guys must have studied about the Otto cycles, diesel cycles, dual cycles and Brayton cycles as well. In the Otto cycles are generally for SI engines. Diesel cycles are for diesel operated CI engines. Then dual cycles, in the dual cycles you have heat addition process at constant volume and similarly at the constant pressure as well. And then you must have also studied a little bit about the Brayton cycle, which are incorporated in aircrafts. Some of the land-based gas turbines are also used. Generally, Brayton cycle is for gas turbines. And then you guys studied about the fuels which are being used in the IC engines. Some alternate fuels you must have also studied about it. Today I am going to start about one of the most important and essential components of the IC engine, and that is carburetors. Alright, internal combustion engines, all the internal combustion engines basically require some fuel to operate. That fuel will go into the combustion chamber where it will get combusted, and then your car will move. Similarly, the first question which arrives in our mind is how are we going to enter the fuel into the internal combustion engine. So there are many techniques, there are many equipments which are being used in the modern cars, but the basic component which were being used in the cars that are operating in the third world countries like Pakistan is of carburetor. Carburetor basically makes the air fuel mixture. Carburetor is basically used for making the air fuel mixture. That air fuel mixture is being sent to your combustion chamber where it will get ignite. This phenomena for the formation of combustible air fuel mixture is known as carburation, because we require different amount of fuel at different times. For example, if I am starting a car, I require some different type of air fuel mixture, and when I am driving a car with a constant speed, then I'll require some other type of a fuel air mixture. And when I'm talking about when I'm accelerating my car, then I will require some different type of a fuel air mixture. We will discuss about the fuel air mixtures in the later classes as well. Carburetor, the purpose of the carburetor is basically to make sure that whatever the requirements are, it is basically sending that fuel air mixture at that particular time. This is the purpose of the carburetor, and that phenomena which is happening in the carburetor, that is the making of a fuel air mixture, formation of the fuel air mixture, that phenomena is called carburation. So the process of formation of combustible fuel air mixture by mixing the proper amount of a fuel with air before admission to engine cylinder is called carburation, and the device which is used for this purpose, which is used for this job, is called carburetor. Okay, another important point which needs to be understood here is that carburetor not only mixes the fuel with the air or makes the desired air fuel mixture, it also atomizes the fuel. Atomization of the fuel is also very important when as the fuel air mixture is inducted into the combustion chamber. Because for example, if I have a high volatile fuel or a fuel which has low volatility, okay, by the word low volatility means it is not going to be vaporized that much easily. I mean, if I compare two fuels like petrol and diesel, petrol is highly volatile, diesel is less volatile, because petrol can be converted into vapors more easily, more quickly. Its volatility is higher as compared to the diesel. So volatility also makes an important factor, means how easily the fuel is vaporizing. So the purpose of the carburetor is to ensure that the fuel not only mixes with the air, but it also atomizes. What's the importance of being atomized? Because if the fuel is not atomized, the combustion will not take place properly. But if the fuel is atomized, there will be for example, they are the two fuel particles, there will be some air particles between them, and they will combust, the air particle will combust the fuel particles. So what is the purpose of carburetor? Now the question is, what is the purpose of carburetor? You can simply answer it by saying the purpose of a carburetor is to form a combustible air fuel mixture of the desired requirement, and not only to make the air fuel mixture, but the carburetor also atomizes the fuel so that proper combustion may take place. Okay. Next we have the factors which affects the carburation. We have basically 4 factors which affects the carburation. We are going to discuss all of them one by one. The first one is the engine speed. Engine speed, for example, if I am running a car at a high speed, then we have a very few time available for the injection of for the preparation of air fuel mixture, and carburetor needs to ensure that whatever the engine speed is, whatever the speed at which the engine is operating, it has to provide that air fuel mixture, it has to provide the desired air fuel mixture. So the time available for the mixture formation is very limited. Therefore, in order to achieve the high quality carburation, and by the word here you must understand this word as well. What do we mean by high quality carburation? High quality carburation, by the word high quality carburation, I meant that how much the mixture, the air fuel mixture, has the vapor content of the fuel. If the air fuel mixture has a high content of vapors, it means it has a high quality carburation. But if the vapor content is low, then it's not a high quality carburation. It means that your carburetor is not working properly and it is not atomizing the fuel. Okay, so it is also very important. The purpose of the carburetor was to not only to make the air fuel mixture but also to atomize the fuel as well. So therefore, in order to have high quality carburation, the velocity of air stream at the point of fuel injection has to be increased. So how do we increase this velocity of the incoming air stream? The question is, how can we increase the velocity of this incoming air stream? And the answer to that question is very simple. You must have also studied in the thermodynamics that if I want to increase the velocity of any fluid which is flowing, I can simply use a nozzle. So here in the carburetor, what we are doing is, since we want to increase the velocity of the incoming air stream, we have a nozzle section which will increase the speed of the air, and that when the speed is being increased, the pressure will reduce, and that pressure difference will allow the fuel to move from one section to another section, and that is into the Venturi section. I will discuss these parts later as well. So what I am trying to say here is that when the engine speed is high, when you have a high engine speed, the time available for the carburation is very low, and your carburetor must be very efficient to provide the desired air fuel mixture. Okay, this is achieved by introducing a Venturi section. Simply, I already told you guys that we will be incorporating a Venturi nozzle type section. Here we are basically using converging, in the carburetors we basically have a converging diverging nozzle section. I will discuss these parts later in my lectures. Then the second factor which affects the carburation is of the vaporization characteristics of the fuel. As I discussed earlier, that highly volatile hydrocarbons, by the word highly volatile hydrocarbon, I explained you earlier that highly volatile hydrocarbon means those hydrocarbons, those fuels which can be converted into vapors very easily. And I gave you the example of the petrol and the diesel as well. If I compare a petrol with a diesel, petrol has high volatility as compared to the diesel. Petrol vaporizes into gaseous state more easily as compared to the diesel. So vaporization characteristic of the fuel is also a very important factor which affects your carburation as well. Vaporization characteristics are generally associated with the distillation curves of the fuel. Distillation curves basically tells you that how much percentage of the vapors will be there at that particular room temperature, at that particular atmospheric temperature. And Dr. Usman would have discussed these distillation curves in the chapter number 6 as well, which was of the fuels. Vaporization characteristics of the fuel. We basically had what are the factors which affects the carburation. First one is the engine speed. Higher engine speeds requires efficient carburation as well, because we have a very less time available for making of that air fuel mixture. The second was of the vaporization characteristics of the fuel. Means you simply require a high volatile hydrocarbon. So the third factor which affects the carburation is of the temperature of incoming air. The higher the atmospheric temperature of the air, it will increase the vaporization of the fuel. Since the temperature is high, the fuel will get the energy, will get the required amount of energy to vaporize from the surrounding, and it will eventually produce a more homogeneous mixture. So so it is basically going, this factor is going as an advantage, that increase in the incoming temperature of air will increase the vaporization characteristics of the fuel, will increase the vaporization of the fuel, and eventually it will lead to the formation of homogeneous mixture, which is the primary requirement or the purpose of the carburetor, to prepare a homogeneous mixture so that your IC engine can have a proper combustion. Another thing which comes in our mind, another question which arises in our mind should be that with the increase in the atmospheric temperature, will it affect the volumetric efficiency? So first we should understand what is the volumetric efficiency. You guys must have studied the volumetric efficiency in the chapter number 1. Volumetric efficiency can simply be defined as the amount of air, the actual amount of air which is entering into the combustion chamber, divided by the ideal amount of air which should have entered into the combustion chamber. Now what do we mean by that? It simply means that when the amount of air which should have gone into the combustion chamber is not same to the amount which has actually gone into the combustion chamber. This can simply be understood by the concept of a density, since the increase in temperature decreases the density of the air. Density is being decreased as the temperature is increased. The same by the decrease in density, you can simply take it as the same amount of a mass will require a larger volume, but the volume of the combustion chamber is not changing. Since the volume of the combustion chamber of your engine is not changing, the same amount will not go into the combustion chamber which would have been gone in the cold weather. The lesser amount of air will be going inside your combustion chamber. So answer to that question can simply be yes, the atmospheric temperature will decrease the volumetric efficiency, because we have a lesser amount of a mass of air is going into the cylinder, which will eventually decrease the volumetric efficiency. So the next point which basically The next factor which affects the carburation is of the engine design. So this factor is simply is associated with the designing of the engine, and for example, the amount of a air fuel mixture, some amount of a air fuel mixture is coming into the intake manifold, and then from that intake manifold it will go into the four different cylinders. So your designing should be in such a manner that the same amount of air fuel mixtures, the same amount of fuel is going into the four cylinders. If the same amount of the fuel is not going, if the same air fuel mixture is not going inside the four cylinders, then you can have some pulsations in the power output as well. You can have some incomplete combustion, improper combustions in some cylinders because of that phenomena. So from the designing point of view, it should be make considerable that you have distributed a homogeneous mixture inside the all cylinders. Alright, next we have some different types of air fuel mixture. We can have three types of air fuel mixture. First one is chemically correct mixture, second one is rich mixture, and the third one is the lean mixture. So the chemically correct mixture are those mixtures in which you have provided the actual amount of air which was required for the proper combustion. For example, if one molecule of a fuel requires 10 molecules of air and you are providing that, then the combustion in that case, in that scenario, would be chemically correct combustion. The combustion will be complete, and that mixture will be called chemically correct mixture, since you have provided that exact same amount of air which was needed for proper combustion. Chemically correct mixtures are sometimes also called as stoichiometric mixtures. So and for example, if a molecule requires 10, if a molecule of a fuel requires 10 molecules of air and I am providing 9 molecules of air for the combustion, in such case the combustion will not be a complete combustion, since the amount of air is less which was required for a proper combustion. So rich mixtures are those mixtures in which you have provided a less amount of air, or you can simply say more amount of fuel. Then we have a third amount of a mixture, that is of a lean mixture. Lean mixture means that if a fuel molecule required 10 molecules for proper combustion and you have provided 12 molecules of air, means you have provided some additional amount of air for combustion. Such type of air fuel mixtures are called lean mixture. So I'm just going to repeat these things again. Repeat these types of air fuel mixture. We had basically three types of air fuel mixture: chemically correct mixture, rich mixture, and lean mixture. Chemically correct mixtures are those mixtures in which you have provided the stoichiometric amount of oxygen molecules for complete and proper combustion of a single fuel molecule. Okay. For example, if you have a single fuel molecule and it requires 10 molecules of oxygen, you have provided that. But if you have provided 8 molecules of oxygen, then it will be called a rich mixture. And if you have provided 12 molecules of air, it will be called lean mixture, since you have provided a large amount of air. Okay, next we must understand this diagram. as you can clearly see that from 9 till you can say 17 at this point, from this point till this point, this is that combustible range of air fuel mixture at which your IC engine can operate. This is the stoichiometric point. This is your stoichiometric point. From here to here you have a lean mixture. You have excess air, and by the word excess air means you have a lean mixture. And from stoichiometric point to the left side you have excess fuel, and by the word excess fuel means you have a rich mixture. So I am simply pointing it out that you have a lean mixture on the right hand side of the stoichiometric point, and you have a rich mixture on the left hand side of stoichiometric point. So, and this is your combustible range, means your IC engine can operate inside this range from 9 to, let's say, 17. 9 to 17 your IC engine is going to operate. But if you provide a much leaner mixture, let's say 18 or 19, then your IC engine, then your car may have incomplete combustion, and it will not operate properly. And if you provide a air fuel mixture which is lesser than 9, let's say 7, 8, then you have provided a very much rich mixture, and it will not burn properly because it has a less amount of oxygen. So since we have a less amount of oxygen, fuel molecules cannot combust. So we can summarize this diagram by saying that when your air fuel mixture is too lean, it will not burn properly. Too lean, something around which is go beyond 17, it will not burn properly. And similarly we can say that if your air fuel mixture is too rich, let's say richer than this limit, means air fuel ratio is something around 7, 8, then your car may not operate properly as well. So this is, however, a limited range of air fuel ratio in a homogeneous mixture, only within which combustion in SI engine will occur. Outside this range, the ratio is either too rich or too lean to sustain flame propagation. This useful range is from 9 to 19 as shown in the figure. One more important thing which needs to be understood here is sustained flammable propagation. We will discuss this sustained flame propagation in chapter number 10 of combustion in details. But I will give you a brief overview about it right now. Flame, by the word flame propagation, it is meant that flame will start from this point and it will move throughout the combustion chamber. As the flame is generated and it is propagating towards the other side of the combustion chamber, this phenomena is called flame propagation. And if you have provided a too much rich mixture or too lean air fuel mixture, then this flame will not propagate throughout the combustion chamber, or you can simply say it cannot sustain that environment. Okay, so if the mixture is too rich or too lean, your flame propagation will not sustain. The carburetor should provide an air fuel ratio in accordance with engine operating requirement, and this ratio must be within the combustible range. Alright, next we have another graph here in which you can see they are basically two graphs. First one is of air-fuel ratio, and on the y-axis you can simply see power output, and it is another graph of air-fuel ratio with a BSFC, and you can simply call it as brake specific fuel consumption as well. It's the short form of brake specific fuel consumption. So we will discuss these graphs one by one. If I am talking about the curve of air-fuel ratio and power output, this is the curve for air-fuel ratio and power output. You can see that if you want a high power, it is coming at this point, something around 12, and if you increase the air-fuel ratio or you are sending a lean mixture, then this power output will decrease. This is the stoichiometric mixture. So this graph is basically telling us that whenever you require a high power, you have to provide a rich mixture. This is the stoichiometric point, and if you go beyond this point to the right side of this point, you get a rich mixture, and if you go left side of this point, you will get a lean mixture. And I'm simply writing it down. You have a lean mixture on the right side, and on the left side of the stoichiometric mixture, we have a rich air-fuel mixture region on the left side of this stoichiometric point. So with this we can simply conclude that the best power will occur at this point, which is lying in the rich air-fuel mixture region. So this graph is basically telling us that whenever you need a high power, which is in the case of idling and accelerating conditions, when you are accelerating your car, you need high power, so you have to provide a rich air-fuel mixture. And when and now we will talk about the other graph, which is of air-fuel ratio and brake specific fuel consumption. Here you can simply see as well that at this point, when the air-fuel mixture is around 16, we have the smallest brake specific fuel consumption, means the small amount of a fuel is being consumed to operate your IC engine, and the small amount of a fuel consumption means that you are operating your engine at the best economy. So whenever you are running your engine under the normal circumstances, under the normal conditions, it is desirable that you run your engine that you are operating your IC engine with the best economy or with the lowest brake specific fuel consumption, means the less amount of a fuel is consumed to produce the work. So for that purpose, you basically in order to obtain the best economy, we have to provide lean mixture. So from these graphs we can simply conclude that maximum output is at when the air fuel ratio was 12:1, means for one molecule of a fuel we were sending 12 molecules of air, and at this point we are getting the best power. Next is for the minimum fuel consumption or for the best economy, the air fuel ratio should be 16:1, means 16 molecules of air should be sent for one molecule of a fuel. It can be noted that the best power mixture is much richer than the chemically correct mixture, and the best economy mixture is slightly leaner than the chemically correct when engine is operating at full throttle. Under the normal conditions, it is desirable to run the engine on the maximum economy. Simply, when you require high power, best power, which is in the case of when you are accelerating your car or you are starting your car from idling condition, you need a high power, so you require a rich air fuel mixture. And when you are operating your car under the normal condition, you require you want to spend less amount of a fuel, so what you do is you want to operate your engine at the best economy. Well, so in this case the best economy is at when the air fuel ratio is 16. Okay guys, so that's all for today. We will continue the topic of carburetor in the next class. Okay, Allah Hafiz. See you next time.